Hello everyone. So we're going to wrap up our class this semester with chapter 17, which is all about the special senses. The special senses are our smell, taste, vision, and hearing. And so they require neurons that are very specific and sensory receptors that are very specific to a certain environmental condition. And so let's get started with this. I'm going to switch over to our PowerPoint. And here are our four major special senses: olfaction, which is smell; taste; visual, with our eyes; and then hearing with our ears. So this video we're going to talk about olfaction, and we're going to jump right into it. So it says this is the neuropathway for olfaction. Olfaction begins in your nasal cavity. We're going to learn that it's a chemical sense. So the sensory receptors in your nasal cavity are going to pick up chemicals that then transfer the information through your olfactory bulb, your olfactory tract, and then into your brain. So your olfactory areas are really generally found in the frontal and temporal lobes, but smell also goes through the diencephalon. So we're going to be examining that a little bit today. So it says Physiology of Olfaction. This is going to be our first handout, 17A. It says that olfaction is a direct sense. So we perceive the sense immediately by our brain. This is what triggers a lot of memories with smell. If you think about it, you can smell something that you may not have smelled for years, but when you smell something, it triggers a memory. That's because it's a direct sense. It says genetic evidence suggests that we can smell hundreds of scents. So we're going to learn here in the next video that taste, we only really have like 5 different types of taste, but we have hundreds of smells that our body can pick up and we can perceive. Now with smell, adaptation occurs very quickly. So what happens is when you first smell something, your sensory receptors are going to fire very quickly. But then we adapt to that, and those chemicals that are triggering your olfactory nerve, the olfactory nerve is going to slow down, and we're going to adapt to the smell. This is why when you first go into something and you smell it, it smells very strong at first, but then as you stay in that area, the smell seems to disappear. A lot of times we can see this with different perfumes, right? So let's say you have a perfume and maybe you have a teenage son, right? And he just douses himself with Axe. Well, that Axe is going to be on his body, and he's going to smell it at first, but he adapts really fast to it. So over the course of a few minutes, he's not going to smell that Axe as much as he did when he first put it on. So what does he want to do? He wants to spray himself again with the Axe because he is adapting to it. Now, the people around him, the people that he walks by, the people that he comes into contact with, they are not adapted to the smell. So they're going to be like, whoa, dude, like lay off the Axe. That's because they haven't adapted to the smell of the Axe. Now, if they stick around him for a short period of time, they will adapt to the Axe as well, and they won't smell it as much as people that he's coming into contact with initially. So this is adaptation. Another good example of this would be when we go into our lab room and dissect those ugly mink. You smell them at first and you're like, whoa, they really smell bad. When you first walk in the room, you smell it. But then after a few minutes, you're not smelling it anymore. That is this adaptation. All right. It also only takes a few molecules of a substance for us to smell it. So if I were to open up a bottle of perfume and set it out, that chemical is going to waft through the air, and it only takes a few molecules for you to smell that perfume. So it says olfactory receptors are going to convey nerve impulses from our olfactory nerve to the olfactory bulb, olfactory tract, and then to our cerebral cortex and our limbic system. So if I go back up to this last slide, maybe, you can see the olfactory nerves are hanging down in our nasal cavity. They connect to the olfactory bulb, which follows the olfactory nerve to our cerebral cortex, and then into the limbic system. All right. So that's the pathway of smell through the nervous system. There is a condition called hyposmia, which is a reduced ability to smell. As we get older, we lose our acuity for smell. So it says about half of the population over 65 have a reduced ability to smell. If you reach 80, you have a 75% chance of losing some of your smell. That's called hyposmia. This might be why grandma over spices her food. So she might put too much salt in it or something, and you're like, whoa, grandma, this is really flavorful. That's because she may be suffering from hyposmia. And so that is an example. It says this can be caused by neurological changes that just normally occur. But drugs, grandma was a hippie back in the 60s, so that may affect her ability to smell, as well as things like smoking. Smoking really affects the ability to smell things, and the olfactory tracts. Because smoking is a chemical, this really does affect this olfactory system. Let's look at Handout 17A next. And as I go to Handout 17A, I want to emphasize that olfactory is a direct sense. So you are going to perceive it immediately. Now, the process of olfaction, it says the first thing that's going to happen is chemicals are going to enter our nasal cavity. So you've got chemicals entering our nasal cavity. These chemicals are going to be sensed by olfactory hairs that are connected to bipolar neurons. Remember back in chapter 12, we said that there are multipolar neurons, there's bipolar neurons, and then unipolar neurons. And I think I told you that bipolar neurons were in our special senses. This is an example of that. So these olfactory hairs hanging down off of the olfactory bulb are going to contain bipolar neurons. They turn the chemical that we're actually breathing in into an action potential. And that action potential can then go to the brain where we can perceive the sense and the chemical that we're smelling. Now, here is a close-up view of this. So these are those bipolar neurons, and those bipolar neurons. Let me get a pointer here. This will be a little bit easier. So these bipolar neurons have little hairs that are hanging down in your nasal cavity. What's really cool about this is these hairs are coated in mucus. So there's a mucus coating around these hairs, or cilia. There's actually it's a cilia. We call them olfactory hairs, but they're cilia that are hanging down. Now, this mucus is going to collect the chemical and hold that chemical next to the olfactory hair. This is why we continue to smell things after we've left that smell. So, for example, if you are in the lab room and you're around the chemicals that are making those mink stink, those mink are producing a chemical that is being trapped by this mucus, and then the mucus is holding that chemical so that those olfactory hairs can pick it up and turn it into an action potential where it's going to your olfactory bulb. Now, when you leave the lab room, you still have some of that chemical stuck in that mucus. So you may smell the mink, minutes to even an hour or so after you've left that lab room. That's because we have to wait until the chemical dissipates out of that mucus so that we don't smell that anymore. All right, so there are mucus lining that covers these olfactory hairs. Now, the next thing that happens is says action potentials are going to move from our olfactory nerve to the olfactory bulb, to our olfactory tract, to the temporal lobe, and the limbic system. All right. So if you look at the pathway here, the olfactory hairs are going to pick it up, send it into the bipolar nerve, which is going to turn this into an action potential. It's going to go to our olfactory bulb, down the olfactory tract, and then into the temporal lobe and our limbic system that connects the cerebrum to the cerebellum. Just realized, let me get rid of that. Sorry about that. Just bugs me. Forgot to get rid of that little symbol. Okay, so the action potential is going to move to our temporal lobe and the limbic system. Now, the temporal lobe is where we're going to store memory of the smell that we have. So you have a memory of what roses smell like. You have a memory of what your grandma's chocolate chip cookies smell like. That is stored in our temporal lobe of the brain. The limbic system is going to play a huge role with dealing with olfaction, because when you think about all of the emotions and memory that smell relays to your brain, that's all going through the limbic system. So smells dealing with mood. They always want you to, if you're stressed out, take a lavender bath and, relax with the soothing smell of lavender, because smell affects your mood. Smell also can affect your emotions. So you can get emotional when you smell things, and it can trigger emotions. It can also play a role in sex and attraction. We are programmed to be attracted to certain smells. It used to be that we were attracted to smells that our body produced. Back in the day before perfumes and that kind of stuff, humans were attracted to body odor. I think this is why some of us are still attracted to, that primal scent that a person's putting out. You ladies really love that hot, sexy firefighter because he's all hot and sweaty and he's putting out chemical attractants. This day and age, we kind of hide those body odor pheromones, but we still produce them. But we kind of find them repugnant now, and that's why we mask things with soaps and detergents and perfumes and colognes. Now, these days, we find those things attractive. So you might have a certain cologne or a perfume that really just drives you wild, and that has kind of taken the place of these pheromones, these natural pheromones, which really is body odor. Body odor is our natural pheromone. All right, so that's Handout 17A. And that kind of gets us introduction to our special senses and our limbic system and how our olfactory affects the limbic system with moods and emotions, and also where it's stored in the temporal lobe. All right. So next we'll go on to our sense of taste, and that will be our next handout.